Okay, good morning, everyone. So let's have a look at this project. So here is the outline of this presentation. So let's go to a very brief introduction. So stainless steel alloys, when exposed to boiling water reactor water chemistry, suffer from corrosion-related phenomena such as radiation field buildup and stress corrosion cracking. So radiation field buildup is caused by the transport and incorporation of radioactive isotopes, which build up on the oxide formed onto stainless steel and causes the exposure of workers to radiation doses. And the main contributor to this phenomenon is the highly radioactive cobalt-60 because it has a long half-life and releases high-energy gamma rays. On the other side, stress corrosion cracking can occur due to the highly oxidizing environment. And in this particular water chemistry called the normal water chemistry condition, the corrosion potential of the system measured is high. And in order to decrease the ECP as well as the stress corrosion cracking occurrence, usually high concentration of hydrogen are added to the water in the hydrogen water chemistry technology. However, high concentration of hydrogen also increase the radiation field. And therefore, an alternative way to decrease the ECP just using a stoichiometric hydrogen to oxygen molar ratio in the water is by using catalytic material like noble metals, which deposited onto the surface of the stainless steel are able to catalyze the reaction between oxygen and hydrogen to form water, and therefore are able to decrease the SCC. In particular, in this project, we used an advanced technology called online noble chem, which consists of the injection of platinum nanoparticles into the water, which by covering the surface of the oxide, are able to reduce the ECP locally. It is well known that the oxide formed onto stainless steel in hydrogen water chemistry has a double-layer structure with an outer oxide formed by a dissolution precipitation mechanism and an inner oxide formed by a solid-state diffusion mechanism. And due to the relative cation's mobility, as well as the solubility of this oxide at this low potential, usually an iron-rich outer layer and a chromium-rich inner layer are formed. And both the layers are constituted by a spinel oxide structure, in which the octahedral or tetrahedral sites are occupied by metal cations according to their preference energy in these sites. So thermodynamics is very useful to explain and understand some phenomena. For example, here you can see the preference energy of the metal cations into the tetrahedral and octahedral sites. And so, for example, here, zinc 2+ is the most stable in the tetrahedral sites, whereas the chromium 3+ is the most stable in the octahedral sites. And if you look at the free energy of formation of the spinel structure, it's possible to predict the most likely crystal formed into a particular environment. This thermodynamic calculation also helps in understanding and explaining some observed phenomena. For example, it has been observed that the cobalt-60 buildup into the oxide can be mitigated by adding zinc ions into the water. And in fact, if we look at the preference energy of zinc and cobalt into the tetrahedral sites, we can see that they compete for the same sites, but zinc being more stable than cobalt, it's believed to can substitute it and reject it into the water, as shown in the schematic on the top. Also, it has been observed that with the zinc injection into the water, usually a thinner and more protective oxide layer is formed. And an explanation for this is by looking at the stability of the zinc spinel oxide compared to the cobalt spinel oxide. So the mechanism, however, behind the beneficial effect of zinc is still under investigation, and therefore this project aims to shed light on the effects of zinc on the oxide properties, in particular when we couple the hydrogen water chemistry with the online noble chem treatment. So the strategy used here is to expose 316 coupon in simulated boiling water reactor water chemistry and then characterize the oxide through advanced characterization techniques. So the 316 coupons were oxidized in an autoclave pressure vessel at high temperature water and in hydrogen to oxygen molar ratio of around 8. In this system, we also inject a metal ion solution, like zinc, cobalt, or platinum, and the ECP of the samples was measured during the test. In the testing metrics here, you can see the sample investigated in this work in particular. So we have a non-dose sample oxidized in pure water, then a zinc dose sample exposed to the injection of zinc, and the third sample is a zinc plus cobalt dose sample subjected to 3 consecutive oxidation stages. So in stage 1 was exposed to zinc injection, in stage 2 was exposed to zinc coupled with the alignable chem treatment with the injection of 1 ppb of platinum, and in stage 3 was exposed to zinc and cobalt injection. So these first 2 samples are useful to understand the effect of zinc on the oxide properties, whereas this last sample has been used to understand the cobalt incorporation in a zinc dose water and after an alignable chem treatment. So we then characterize the oxide via complementary technique. So we use SEM for a qualitative analysis of the morphology and composition, and hard X-ray photoelectron spectroscopy to quantify the elemental composition, assign chemical state, and do some depth profiling of the surface. In particular, AXPES is a surface-sensitive technique which allows the calculation of atomic concentration by using high X-rays. And then these extend the sampling depth up to 5 times deeper compared to a normal XPS. And so you can also detect the deep core level photoelectrons like the 1s. And also, by tilting the sample with respect to the incident X-ray, it's possible to trace the depth profiling of the composition inside the surface. So let's now have a look at the results. So here you can see the SEM images of the top and the cross-section of the non-dose sample. So you can see this coarse crystal light on the top surface, and here in the cross-section you can recognize the double layer structure. In the zinc dose surface, we have a reduction in the size of this crystallite, also a different shape. And you can see that now the oxide is thinner, and we calculate on average a reduction of the thickness of about a factor of 3. Then when we expose these 2 samples to the alignable chem treatment, you can see now the platinum deposition. These bright spots here indicate clusters of nanoparticles of platinum covering the surface. But actually, what we observe is that the alignable chem treatment actually did not influence the morphology of the oxide. Then the low voltage SEM EDX compositional maps here could suggest the composition of the inner and outer layer. So in the no-dose sample, you see this chromium-rich inner oxide layer in blue, whereas the outer layer is composed of iron base and nickel base spinels. So this suggests the presence of magnetite and nickel ferrite on the top surface. Whereas on the zinc dose surface, you see a chromium and zinc rich inner oxide layer, and the outer oxide spinels are a mixture of zinc and nickel. And the magnetite is present in very lower concentration. Again, when we subjected these 2 samples to the alignable chem treatment, we didn't observe a significant difference in the properties of this oxide. Again, on the non-dose sample, you see this magnetite spinel that dominate the surface and the nickel ferrite spinaling ring. Whereas in the zinc dose sample, you see this nickel and zinc ferrite spinel, and the presence of magnetite is very low. In order to confirm the composition of the top surface, we use AXPES, and here is the survey scan extracted from the analysis of the 3 samples. If you look at the binding energy here, you can see that it's extended up to 10 kiloelectron-volt, which means that this analysis allows the simultaneous detection of high binding energy and low binding energy core level photoelectrons. And this is important because the high binding energy core level photoelectrons, so the 1s, having a lower kinetic energy could give insight up to a shallower sampling depth into the surface, whereas the low binding energy core level photoelectrons, so the 2ps, with a higher kinetic energy, give information deeper into the oxide. So by looking at the survey scan again, you see that we detected nickel 1s, iron 1s, and chromium 1s on the 3 samples, whereas in the inset on the right, up to 3 kiloelectron-volt, you can see the difference in the peaks detected on the 3 surfaces. So as expected, on the zinc dose, zinc plus cobalt dose sample, we detected zinc peaks. And after the alignable chem treatment in this 3rd sample, we detected also platinum peaks. By extracting the high-resolution peaks from the survey scan, it's possible to assign chemical states, but also calculate atomic concentration of the elements. Here is the high-resolution peaks for the non-dose sample, and we divided it so in low binding energy peaks at the top and high binding energy peaks at the bottom. So the main peak of the oxygen corresponds to lattice oxide, confirming that we have an oxide layer on the top. And then we found here magnetite presence. And these peaks here correspond to metal oxide peaks. So we have iron, chromium, and nickel oxides. However, because there is a lack in literature about these 1s binding energy peaks, it's not possible to compare and identify exactly what this is. But it's expected a mixture, of course, of these oxide spinels on the subsurface. And we found also some metallic nickel. In the zinc dose sample, again, we observed the same kind of structure. Of course, the concentration of the magnetite was lower, and we have more zinc ferrite on the top surface. In the third sample here, again, we observed zinc ferrite, and most important, we found cobalt oxide. And the noisy signal here reveals a very low percentage of cobalt found at the shallow with sampling depth on the top of the surface. And as expected, the metallic platinum from the platinum nanoparticles from the alignable chem treatment. Then we perform an angle-resolved dark space analysis in order to trace the depth profiling of the concentration of cobalt and zinc in particular, and we compared these two samples, so the zinc plus cobalt dose samples in red and the zinc dose sample in blue. And we observed that the cobalt decreased in concentration going deeper into the oxide, and zinc showed an opposite trend. And this opposite trend of cobalt and zinc might be possibly associated to the immiscibility of these two cations in the spinel structure, and therefore could suggest that the substitution of cobalt with zinc ions is possible. Let's now just recap the main results obtained so far. So we have seen the effect of zinc injection on the oxide properties, and what we observe is that the magnetite was dissolved in presence of zinc ions, so zinc could substitute iron to form more stable ferrite spinel on the outer layer surface, where stable zinc chromite spinel are formed into the inner oxide layer. And therefore, this could suggest that zinc could act together with chromium as a diffusion barrier for the metal ions into the oxide, and therefore form a more protective and thinner inner oxide layer. Then we explored the effect of zinc on the cobalt incorporation mechanism. And this sample in particular was subjected to 3 consecutive oxidation stages. So we first inject zinc to form a very protective oxide. Then we inject platinum together with zinc to stabilize the protective properties of the oxide forms in the previous stage. And then we inject cobalt together with zinc. And what we observed is that the incorporation of cobalt was just on the outer surface of the oxide. And this could be something good, but actually this could be associated with a very protective oxide and formed by the zinc. To conclude, so these results suggest that zinc improved the corrosion resistance of the 316, creating this protective oxide and acting with the chromium as a diffusion barrier for the metal ions. And the alignable chem treatment help in stabilizing these protective features of the oxide produced under zinc exposure. However, zinc demonstrated to not completely suppress the cobalt, at least in the outer oxide, and therefore an improvement to this technology is required in order to mitigate the radiation field buildup. So I would like to thank Hitachi and the EPSRC Green CDT for sponsoring the project, and the Harry Royce Institute for providing the facilities. And thank you very much for listening.